The development of biologic cartilage repair started with the groundbreaking work of Daniel Grandi and Lars Petersen in the 80s of the last century. The clinical impact really showed after the publication of the first clinical cases by Dr. Mats Brittberg in 1994. Since then, first small centers and then more and more centers all over the world worked with chondrocyte transplantation, which means that cartilage gets restored by cultivating chondrocytes and transforming the chondrocytes to produce autologous new cartilage. And this technique has been performed many thousand times, and we have 10-15-year results now showing that the quality of the cartilage is very well in comparison to the original cartilage. And we have seen now newer developments since about 10 years to make it more stable, this technique. In the first steps, you had to transplant a periostal flap onto a defect, and then the idea was to develop a more stable and more reliable technique with the use of scaffolds, three-dimensional materials which resorb over time and allow the chondrocytes to regrow the cartilage. And this is called the second and third generation biologic cartilage repair. And since about 2 or 3 years ago, we are working with the use of a matrix, a three-dimensional matrix, and the cell source is the bone, the subchondral bone, which gets opened, and the cells from the subchondral bone are steered towards a cartilage regeneration. This is the third and fourth generation of cartilage repair. Since I'm working in the field of cartilage repair since 1994, we treated about 700 to 800 patients with various techniques of Alpha chondroshield is one of those three-dimensional matrices, and it achieves its goal in restoring cartilage by collecting the cells and the fluid from the subchondral bone into a cartilage defect. So it serves as a pool for those bioactive cells coming from the bone, and gives them stability until the cartilage regeneration is finished. In my hands as a surgeon, I look for, number one, of course, the biologic performance, and there are quite a few products out there doing more or less the same. For me as a surgeon, it is important to have a material on hand which I can use in the operation theater. It means that it has to be stable enough, the handling has to be good, and that I can treat all the indications I want to treat. And when you look at the material, it's quite stable and easy to use for my purposes. As I said before, the biologic performance counts, and for us it's interesting to see that the material in the degradation process in the body does not leave any toxic traces. This is the most important thing. Number two is that the degradation rate goes along with the new regeneration of the cartilage, means that the material degrades at the same rate as the new cartilage regenerates. And this is important from the biologic point of view, and as I mentioned before, for me as a surgeon, it is important how the handling in the operation theater actually is. That I can cut it according to the size of the defect, and that it's stable enough to be implanted arthroscopically. It's a good approach. You do it for two reasons. Number one is that you want to increase the biomechanic properties of the implant by adding hyaluronic acid. You smoothen out the surface. Number two could be with the PRP that you enhance the immigration of cells from the subchondral bone into the scaffold and therefore increase the rate and the quality of the cartilage repair. I sometimes don't add anything to it, and it seems to work as well. But this will turn out to be a whole new field for developments in the future by adding, for example, growth factor or other materials to it. The most important thing for the fixation is definitely the preparation of the cartilage defect. You have to identify the cartilage defect, assess the actual size, and it's usually more than you actually think. On this picture you see how the cartilage flows into the defect. There it is important to create a stable wall from healthy cartilage, which creates a bed for the implant, for the matrix you want to put in there. And the second step is that you debride the bone, the underlying bone, remove all cartilage debris from the floor of the defect in order to create a stable surface where you can put your matrix on. Those are the first steps before you start actually fixing the matrix. The second step is to open the subcorneal bone. This is a microfracture technique which is well known. You use the specific materials, as you can see on this picture, to open up the subcorneal bone and induce bleeding from the bottom up. New researchers showed that it might be beneficial for the quality of the cells if you use a small drill and go about 1 centimeter deep into the subcorneal bone to get a better quality of the cells. Future will show whether this is actually true. And the third step would be then to measure the size of the defect according to the defect lesion, and then cut it out and put it into the defect. Make sure that it's smooth on all sides. And then you have various possibilities to fix it. Either you just glue it in with a little bit of fibrin glue. For well-contained lesion, you can just put it in and let it sit, and it sticks to the ground due to its adhesion properties. And more stable ways to fixate it is either with transosseous sutures. It's a very stable but not so easy technique. The details you can look up afterwards. And the third possibility is that you use resorbable pins, a very elegant arthroscopic method which delivers a very stable fixation of the implant. All patients with painful cartilage defects. Number one, it's important to find out whether the cartilage defect is actually the problem. And when it's identified with MRI and you know the size and the shape of the defect, then you can decide whether this is a candidate for an ACS treatment. I usually use it for patients with smaller to mid-size defects between 2 and 3 up to 4 square centimeters of size, and full thickness means all the way to the ground. And then I can decide whether I will perform this technique arthroscopically, which is possible in most cases, or open for larger lesions, more than 4 square centimeters, or way far in the back of the knee joint, which is hard to reach arthroscopically.